Welcome to my new calculus channel. My name is John Gabriel. And in this particular video, I'm going to be discussing the tangent line problem and showing you another video of the mainstream viewpoints. But first, I want to tell you that neither Newton nor Leibniz actually knew exactly what they were doing. And what is a tangent line problem about? Well, it's a problem of trying to find the tangent slope at a given point, okay? So basically, the slope of this yellow tangent line, okay, is what we're trying to find. So if you had to look at this for the first time in your life without having learned about any calculus before, just like Newton did, it would be quite a humongous problem. It would be incredibly hard. In fact, so hard that nobody before I came along was actually able to solve it in a rigorous way. So what did Newton and Leibniz do? Well, what they did was they started calculating the slopes of the secant lines, this broken dotted red line here, the slope of the secant lines as it got closer and closer to the tangent line. Okay, so in other words, as this secant gets smaller, its slope begins to resemble more the slope of the tangent line. And that's precisely what Newton did in order to calculate the slope. But it didn't stop there. He actually used this finite difference quotient, which is, in fact, never the slope of the tangent line, but always the slope of one of these red secant lines, okay? And approaching from either side because it doesn't really matter. So he used this finite difference quotient and considered what happens when h becomes very small. So h is really the distance between the blue point of tangency and the green line. So as h becomes smaller, then obviously that secant line starts to resemble more and more the yellow tangent line slope, right? So now this is what Newton did. He just went ahead and substituted the functions inside the finite difference quotient and actually found the slope by setting h to 0 after he had simplified the difference quotient, okay? So, and by the way, don't hear a single bit of crap that your professors tell you that it has nothing to do with setting h to 0. They may say that, and they may try to look at it this way, but it has exactly the same effect as setting h is equal to 0, okay? So, in other words, once you've simplified this quotient here and you set h equal to 0, you've actually found the limit. But it's a bogus method because before you simplify the difference quotient, h is not 0. And afterwards, it is 0, even though they tell you, oh, no, we never set it to 0. We just consider the ratios as they approach some limit. But they don't even know what that limit is unless they violate the rules and actually set h to 0. Okay, so there is no rigorous way in the bogus mainstream calculus of finding the derivative. I was the first with the new calculus to produce a rigorous formulation. But now, and of course, you know what happens as this point here gets close to the point of tangency. You end up not being able to evaluate it. So the limit is presumably the value that exists once you get to this stage here. Okay, so there is no way in your bogus calculus to find it systematically. All right. So now let's take a look. Let's take a look at a video that I want to critique because I think that this is a good way of showing you how ignorant and wrong mainstream academics are. So at 2.7, which is about there, let's go there, he says,
corresponding with a rate of change. For example, if we're talking about this graph, this is the graph.
So what he said there, he said the slope is talking about the slope of a tangent line corresponding with the rate of change. That's absolute nonsense. The slope of a tangent never corresponds with any rate except a particular ratio, which happens to be its slope, okay? So the idiot mathematicians of the last 400 years or the last 150 to 200 decided to call it a rate of change. And one of those big baboons in the Church of Academia is Professor Gilbert Strang from MIT, and the many misguided books he has written on calculus, okay? So in fact, there is no such thing as a rate of change in calculus. Even when a time differential is involved, nothing is actually changing because a particular model is used. So the slope of a tangent is never anything but a ratio, the ratio of rise over run, okay? And then at 42, let's see, at 42, what does he say here? Okay, let's listen.
Rise 1 while we run 2. So in this little graph, we have a slope of 1/2. And we can think of it in terms of change if we have an example like, oh, maybe this is the graph of some.
So he says we can think of it in terms of change. No, we can't, because nothing is changing, okay? Rise over run is just a ratio that was used by Newton to describe the slope or inclination or gradient of a straight line. And there is no change anywhere in the graph. All the tangents have been there since past perpetuity and shall continue to be there even if no life, no sentient life, or any life ever existed. In fact, these concepts exist independently of anything else. They are self-contained. They are immortal, right? Now, at 110, he says, it talks again about rate of changes, and I'm telling you, I've just mentioned this, that even when time is involved, nothing actually changes because the graph is a model, and the elephant population is just the value of a graph at a certain point. There is no such thing as a rate of change at a point, okay? And furthermore, at 1 minute and 38, there is no such thing as rate of change because nothing is changing. All the points are the same, all the tangent lines are the same, and all their slopes have been the same. And rise over run is not a rate, it is a ratio. Change at 217, change is not relevant, and how fast or how slow is also irrelevant. The graph is not changing at any point. The x and y coordinates of every point are the same. The tangent lines are the same. Nothing is changing. So the notion, and then he says at 226, the notion is that on a curved graph, the rate of change changes. Now that's the first red flag there. So the rate of change changes. That's actually totally incomprehensible because first of all, there isn't a rate of change because nothing is changing. And nothing is changing doesn't change. So actually, nothing changes at all. And all those ratios are fixed. There is no rate of change at a particular point, as the idiot claims, only a possible tangent line with a slope that can be expressed as rise over run. Now at 452, he says the slope of 3 is then an approximation for the slope of the tangent line at the point. Oh dear. So let's just watch that quickly. 452. 452 is here. Let's get there. So 452, here goes.
Slope of the tangent line at that point. Now,
So he said the slope of 3 is then an approximation for the slope of the tangent line at that point. So he's no longer referring to it at a rate of change. What's going on here? What a moron. Okay. So in other words, they've just taken the slope of the tangent line and called it a rate of change. But there is no such thing as a rate of change. Do you get that? It's a myth, it's an illusion. And at 8:21, 8 minutes and 21 seconds, it says, the closer we get to x, the better the approximation of the tangent line. Yeah, that's what I was describing to you at the start of the video. So we want the limit. Now, this is the crazy part. So we want the limit as ... to get the slope of the tangent line exactly to be the amount we want it to be. wow. So I didn't know that you can actually want things to be in mathematics, and that's how they ought to be. That's not how things are done in mathematics. It's not what we want, it's what the facts are. So I find that extremely funny. How can you get the slope to be the same as the tangent line slope, which is what you're looking for? Excuse the circularity, folks. Of course, the morons in mainstream academia use the bogus first principles method, which is in turn part of its own definition, and no mention at all of what is the limit. For example, is it a rational number or some magnitude that cannot be measured, such as pi, e, or square root 2? So this fake formula for the derivative in mainstream is basically not only circular, but it requires that you know the limit. And the only way you can find the limit is using your bogus first principles method, okay? And the first principles method contains highly invalid arithmetic. And in fact, you cannot find L unless you set H is equal to 0. That's the only way you find L. And it's completely circular. So at 9 minutes and 4 seconds, he says, in order to evaluate the limit, we need to know the function, and let's evaluate the difference quotient. Well, you're not really evaluating anything. When he says, let's evaluate the difference quotient, he means the first principle methods. In other words, assume H is not 0, do the division, simplify everything, and then set H is equal to 0. That's how you evaluate the limit, okay? And obviously using the function. So the first principle method is definitely bogus. And now this guy here has a very well-viewed channel of 123,000 or almost 124,000 views. I commented on the channel, and the damn idiot didn't print my comment. It shows my comment there, but only I'm actually allowed to see it. So of course he's not going to print my comment because it exposes all the bullshit he's talking about. And there's a good reason he doesn't want to print my comment, namely because if you don't go to his site and buy one of his math courses, he loses out. So he doesn't really care whether you actually understand anything about calculus or whether anything you've been told is true or not. In fact, he doesn't even know the difference between truth and lies. He's simply regurgitating the rot that his professors talk to him about. So at any rate, this tangent line problem has been around for almost 380 years, almost 400 years, and I was the first to solve it geometrically. You can find a general proof of this. Let's see here. General proof of derivative. Let's see here if I can find it. New calculus. You get all these other crap videos coming up. Where is it now? Oh dear, can't find it. Here it is, here it is. So this is the one that tells you how you can use sound algebra to find the derivative definition, okay? So this is a proof using sound algebra. And of course, also the new calculus integral doesn't use infinity or rot like that. And everything in the new calculus is based on well-formed concepts, right? So I explain to you how to do all these things, and I show you how it works in terms of similar triangles and how this could have been realized over 2,300 years ago. So I encourage you to download my free ebook on calculus. It's the most important mathematics book ever written, and study these things and learn about the well-formed definitions in the new calculus. So I hope you've enjoyed this little presentation on the tangent line problem, and that you will join me again in the near future for another interesting topic. Thank you very much. My name is John Gabriel, and this is a New Calculus channel. Till next time, goodbye.